Good afternoon, and welcome to the Osher Lifelong Learning Institute at UCSD. I'm Jerry Kent, member of the Curriculum Committee and host for this afternoon's presentation. As we grow older, we're all acutely aware of how important our senses are. The one that gets short shrift is that of touch. I was recently watching my granddaughter, who's just 3 now, and she seemed to revel in touching all the different kinds of surfaces that are around. And the response from her, for things that were smooth and soft, she would be elated, but things that were kind of prickly or scratchy or rough, not so much. And so it was interesting to me to watch this developmental thing. And today we're going to learn something about tactile sensations and how these might be simulated and brought into virtual reality. The lecture today by Professor Darren Lipomi is going to deal with that subject, and he is an associate professor of nanoengineering at UCSD and received his PhD in physics and was a postdoctoral fellow at Stanford. While there, he earned a certificate in innovation and entrepreneurship, which is a kind of an extended thing that leans over to the business area. He studies all manner of exotic organic materials, especially those that are mechanically compliant and have electrical properties. Darren is extensively published and has received numerous national awards. He'll discuss these materials and how these can facilitate man-machine interactions. Please join me in welcoming him for today's lecture. May I say, touching lecture.
Thank you, Jerry, and thank you, Steve, very much for the invitation to be here. It's really a pleasure to take a short walk across campus from nanoengineering and to be with you all today. So, what is nanoengineering? How did I arrive in a department called nanoengineering? I've only been at UCSD for 5 years, a little bit less than 5 years actually. So where I came from is still very much shapes the kind of work that I do. I was an undergraduate at Boston University in chemistry, and my first language is actually organic chemistry. So the chemistry of carbon and nitrogen and hydrogen, and how they combine to make molecules with interesting functionality. So while I was a student, an undergraduate student, I made these molecules called basiliscamides A and B. Say that 5 times fast. And what they did is they have antifungal properties against organisms that adventitiously attack patients with compromised immune systems. From there, I did my PhD at Harvard in a group that was really founded on organic chemistry, but I didn't do any organic chemistry in the lab. I did a topic called nanofabrication engineering, and we were very interested in a range of different topics, but in particular, what we wanted to do is make large areas, and on the nanoscale, large means a square millimeter. So large areas of little metallic particles that interacted with light in a certain way to reflect it and refract it and to give you chemical sensing surfaces and other types of function. From there, I did my postdoctoral stint at Stanford in the chemical engineering department. And at Stanford, my research was funded by the intelligence community, and the topic was making devices that had the characteristics of being transparent, conductive, stretchable, and sensitive to strain and pressure. So electronic skin, but transparent, combining a lot of properties that don't like to coexist in one type of material. And that's really a recurring theme throughout my research. And while I was funded by the CIA, and we got a tour of the CIA headquarters in Langley, the tour consisted of 3 rooms: the lobby, the gift shop, and the cafeteria. So while at Stanford, I had the opportunity to work on a number of different projects. This is the stretchable transparent pressure sensor, and while an iPhone or a smartphone is sensitive to touch, this was also sensitive to pressure as well. Now iPhones are now sensitive to pressure as well, so we might have been a little prescient here. We also made a device that we were able to insert into a mouse brain to measure the pressure of intracranial pressure that arises in humans, for example, after an accident or in military and intelligence gathering missions. And what ends up happening is that patients leave the hospital and their brain swells afterwards, and they develop injuries several days after being released from the hospital. So this is an implantable wireless device that could measure the pressure inside of the mouse brain. These inventions were patented. Unfortunately, well, I shouldn't say that. Not by UCSD, but Stanford is the assignee. And anyway, another device that I made during this time was the first stretchable organic solar cell. And why on earth is that interesting or compelling at all? Hopefully, I'll make a point before getting to the main topic, which is artificial touch. So this is the topic of organic or plastic semiconductors. Semiconductor, just the material that a chip is made from in a computer, and the idea is, can you take one of those and stretch it out while it still retains all of its computational function? And to do that, one of the goals is to use organic materials, so plastic materials that have deformability, like the top of a Tic Tac container, anything else that's melt processed and also flexible and even stretchable. So if you take ethylene, this is just two CH2 groups bonded together by a double bond. And in chemistry nomenclature, it's ironic that organic chemistry is the chemistry of carbon and hydrogen bonded together, but ironically, you never write carbon and hydrogen. You only write the bonding arrangement. So ethylene is this thing, just this equal sign to represent the two bonds. And polyethylene is taking the bonds and linking up the atoms. So you take one of the bonds, you make a bond with a second one, then a second one. It's like a cascade chain reaction to make this polyethylene, and it's an insulator. It looks like this in pretty highly crystalline form, but it's also the same material that milk jugs are made of and a wide variety of commodity products. Now you add one more bond, and you go from ethylene to acetylene. Now you have C triple bond C. And if you polymerize this, you still have another bond left over. And this makes a structure called polyacetylene, which, believe it or not, is a conductor. So these double bonds that alternate along the backbone structure allow for charges to spread, and they can be moved in an electric field to conduct electricity. And these look a lot different. This is like a metallic foil made of polyacetylene, and you can do a lot of neat things with these types of materials that are called semiconducting polymers or plastic semiconductors. You can make solar cells and field effect transistors and light-emitting devices. In fact, organic light-emitting devices are now a billion-dollar industry. Samsung makes these routinely. You can go to Best Buy and get an OLED TV. If we look only at the solar cells for now, the organic solar cells based on this type of material are now more than 10% efficient, which is quite good. And in fact, the charge, the quality of with which these materials transport charge is in some cases better than the bad types of silicon, but the silicon that is made in very thin, transparent forms. So one of the groups that we work with, led by Frederick Krebs at the Danish Technical University, made these solar cells made from organic semiconductors and deployed them in rural Africa for part of the Lighting Africa initiative so that kids could do their homework after the sun goes down without burning biomass unsustainably. But what the researchers found was that mechanical failure mechanisms were dominant during the field test. And the National Science Foundation and Office of Navy Research had a workshop, this is now a few years ago, but this question is still an outstanding question, that asked, how do these cells fail mechanically? In fact, they fail mechanically before they fail from being out in the sun. So normally, organic structures want to be converted to carbon dioxide. Ultimately, anything made of carbon is going to be CO2 eventually if given enough time in an oxygen environment. But these devices, if you twist them and bent them, they failed faster than the photochemical degradation. So on the left, we have the current and shorter term goal. But on the right, we have the longer term goal. And that is to endow these materials not only with mechanical resilience, but also other properties inspired by biological tissue, like the ability to self-heal, the ability to biodegrade, the sensitivity to touch and to chemical signals. So the idea is really to make Mr. Data from Star Trek a reality. And about a year ago, my work was written about on the National Institutes of Health Director's blog, and my sister tweeted the story. I didn't have Twitter at the time, but my sister tweeted the story and tagged Brent Spiner, who plays Mr. Data, and he retweeted it to 1.5 million followers, which was the happiest day of my career. But the problem is still that as you stretch these materials, they don't have skin-like elasticity. They tend to fracture, like this image in the bottom right. So how are we going to solve that problem? Well, there will not be an exam on this chemical structure. I just want to give you an idea of the approaches that we're taking. So this is not polyacetylene. It's got a few bells and whistles on it compared to polyacetylene. But what it does have is a biodegradable elastic segment, a semiconducting segment, other segments on it that allow it to accommodate mechanical deformation. And we're quite on our way to making a material that has all of these properties. And not just mechanical deformability like human skin, but also sensitivity to pressure and other analytes. Biodegradability, you put it in the body and it decomposes into harmless byproducts. Still working on that, but at least it works in a flask. And the capacity for self-repair as well. And we have a number of ideas of what we might use these materials for in biomechanical sensing and artificial retinas and other applications. Now, what is our approach? We have many different approaches that all work together to try to give us this type of functionality. So we are making materials in a flask because my first language is organic chemistry and I really want to actually make stuff. At the end of the day, you kind of have to put something in a bottle. But we also do device testing, and interestingly, now we have two students who do mechanical modeling using the San Diego Supercomputer Center, which is just a couple blocks from here. And what we're able to do is enter the molecular structure, and my student has software that will predict the stretchability and toughness of these materials just from the molecular structure by making these simulations that are called molecular dynamics simulations. So what are some of the aspects of these materials that we test? One of them, and this is probably the simplest one, is just how long is this polymer chain? How long is this single molecule of plastic going to be, and what is that going to do for us technologically? Well, it turns out if you have super long strands of spaghetti, they tend to tangle up. So we call those entanglements, and we can use theory to calculate the entanglement density, which is on the right. So this is how many knots have kind of been formed in the material. And if you look on the left, if you go from green to blue to red to black, that is more entanglements, and you can stretch out the material even farther depending on how long the material is. And you can use the chemistry to tune how long the chains are going to be. Another molecular characteristic we look at, which is the length of this group right up here. And this group here that says CnH2n plus 1 is called a side chain. And the side chain is there so that the material is soluble. That's its only purpose. It's so that if you make a paint formulation out of this material, you can coat it onto transparent sheets for solar cells, or you can pattern it into a TV, for example. But you always need this side chain here. Now with the side chain, you get changes in the properties. The longer the side chain is, the less stiff it becomes. So this is a plot of the tensile modulus, which is like the stiffness, versus the length of the side chain. So the stiffness goes down as the length of this side chain goes up. So those are some of the characteristics that we exploit in order to make our materials more like skin. So one of the things that we can do is, if you have, for example, a material that's flexible, you can bond it to a cylinder or a cone because it only needs to flex along one axis. But if you want to take the same material and put it on the top of your head without wrinkling, without the material wrinkling, then you need to have stretchability as well. Flexibility alone won't work. It needs to stretch out in order to get something onto even something as simple as a hemispherical surface. So what we wanted to do is make this R2-D2-like solar cell. And it's basically a normal solar cell, except that we had to stretch out the material in order to get it to be this shape. So if we do a model, we found out that we needed a certain amount of strain. It turns out we needed to stretch it at maximum by 24% in order to get this thing to bond. And we found that the shorter side chain gave this cracked version, and the longer side chain gave us this intact, uncracked version. And this is what the output of the device looks like. It's not a very good solar cell, but it's a solar cell, and it's the first hemispherical solar cell. So can we go one step further and take everything we know about making devices, and can we bond them to the skin to power wearable devices? So it turns out to do low energy communication, there are some people at UCSD that can run really, really low power radios and circuits that require nanowatts. So even just the light from this lamp might be enough to charge up my device for all day. So if you can get a little bit of a solar cell on the wearable device, of course the skin is stretchy and it bends. So can you use these structures to make cells that will bond to the skin just like a sticker, but it will generate electricity? And this is my student's wrist, and he squeezed the cell on his wrist 1,000 times and powered this watch. And now this is just a research grade device, so this is an impressive accomplishment for us. You notice the watch with the battery taken out says 1201, which means that this device that we just put together in the lab has been working for at least 1 minute, which is good for us. That's right. This is the kitty hawk of wearable solar cells. We can also take one step further and make all the components out of rubber. And I think that this is the first ever semiconductor device in which the encapsulant, the substrate, the encapsulant, the anode and the cathode, that's the positive and negative terminal, and the semiconductor layer are all made out of rubber. So this is a rubber solar cell. You can step on it, you can throw it across the room, and it's going to survive just fine. Now, those are sort of little cute laboratory demonstrations, but we're also building robots in the lab to do endurance testing of entire modules. I know this gets a little bit far from my skin-like properties and virtual touch, but I wanted to show you. This is a solar panel that's a yard long. And this is a robot, we call it Bender, that bends these cells millions of times, literally millions of times. And you can also reconvert it to a twister. And what we're trying to do is develop materials that will survive these processes, so that we get sound with this one, and so that they don't rip like this. So that's well on its way to working. But one of the problems that we have is that we're stuck with these very large, very thick encapsulation layers, which actually concentrate strain on them when you stretch them and bend them. So can we make something that's a really thin encapsulation layer? Now there's a material called graphene. Now graphene is a single layer of carbon atoms that has an architecture like chicken wire. So it's little hexagons of carbon atoms, and it is one of the strongest and most conductive materials known to science. But the problem is that the current graphene fabrication methods, manufacturing methods, they take a film of super pure copper foil, and it costs a lot of energy to make it. It's 20 to 100 micrometers thick, that's millionths of a meter. Then you deposit this single layer of carbon atoms on top, and then you chemically etch in a toxic acid bath the copper away, and then you get this one layer of carbon atoms for the graphene. Now this takes about 10,000 grams of copper to produce 1 gram of graphene. Now ironically, we call the copper a catalyst, but it's really much more than a catalyst, and it's not a very green process. So my student came up with this method, and the basic idea here is that you can strip the graphene off the copper while leaving the copper safe for another cycle of growth. Now it took a long time to be able to figure out how to strip the graphene off because copper and graphene hold on to each other really tightly. But what he did is we patented this, and he started a company which is now based in Scripps Ranch, and he and his business partner raised $1 million seed A financing round, and actually they sold their first product last week, and my research laboratory was their first customer. So that might be a conflict of interest, but I'm pretty sure the lawyer said it was okay. Now, because we were used to depositing graphene on metals on graphene in order to do this transfer, we found a really interesting thing. So you're all familiar with Scotchgard coatings and coatings on windows and eyeglasses that allow rain to bead up on them. It turns out that graphene is a little bit like a Scotchgard coating, but if you change what's below it, so you change the windshield for a different windshield, the ability of graphene to be a Scotchgard coating changes a little bit. So if you have something that like glass and then graphene, the droplet of water will spread out a little bit. But if you have plastic, then graphene, then the droplet of water sees through the graphene and beads up, just like it would on plastic. So that's a really interesting phenomenon. It's called wetting transparency. And what we did is we found out that this works not only for water droplets, but also for thin films of metal. So we can make this zoo of metallic nanoparticles that are very closely spaced. So by nanoparticle, I mean characteristic dimensions of a billionth of a meter. Now, what's interesting about having particles that are closely spaced is that the conductivity between these little metallic islands is mediated by something called tunneling, where an electron can end up on an adjacent metal nanoparticle without us doing much of anything. But the tunneling probability, the probability that that's going to happen, changes exponentially based on the amount of stretching that these things undergo. So you can see my interest in thin things and stretchable things is leading me to an idea here. So what if we could make a sensor based on these graphene and nanoparticle films that were very sensitive to stretching? It turns out we can do that. So this is a schematic drawing of a piece of glass with a thin piece of tape. It's a plastic tape that's heat resistant, and it's called Kapton, and you can buy it at a hardware store. It's 13 microns. It generates a very small step between the step edge of the tape and the glass slide. If you take your graphene film with the metal nanoparticles and you put it right on the step and you press down, you generate a very small strain right at the edge where this thing is, where your film is being bent. The film is being bent right at the step edge between the tape and the glass. That generates a strain that's 1,000th of 1%, and we can measure that. Now, that amount of strain is equivalent to taking something the thickness of a human hair and stretching it by one atom worth. That's how sensitive we're talking. So you can take one of these one of these films, put it right on your wrist, and the pulse pressure in your wrist will actually cause the particles to deflect, and you can measure the pulse using this as a sensor. There's a problem in drug discovery, and I'm not in this field, but people that collaborated with us tell me that this is a big problem, that a lot of drug candidates are thrown out early on in the process of toxicity screening because of suspected cardiotoxicity. So what we wanted to be able to do was measure the effect of the contractility of heart muscle cells, so how strong they beat, using strain sensors based on these graphene with these metal nanoparticles. So these are some neonatal rat cardiomyocytes, so they're rat heart muscle cells, and in the top left, this is a video of a collection of them beating with the graphene nanoisland film butter side down, so the nanoparticles are on the bottom, the cells are adhered to the graphene. The cells like graphene for some reason, and as they beat, you can measure the change in resistance of the film while the heart muscle cells beat. So this also became a patent which was licensed by our company Groltex, and hopefully they will be developing it into a technology. Now that's an in vitro application. Is there any way in which we can use the strain sensing on an application outside of our bodies to be diagnostic devices or even a therapeutic device? So we were approached because of this work by some researchers at MD Anderson Cancer Center, and in particular, one of the researchers, who's a psychologist, her name is Eileen Shin, studies the patient compliance with postoperative exercises. Now, for head and neck cancer patients, they are asked sometimes after radiation therapy to do swallowing exercises when they go home so that their swallowing muscles don't develop fibrosis, because if you don't use it, you lose the ability to swallow. So the idea was, can we make a patch that connects to an iPhone that measures the ability to do these swallowing exercises? So this is my student's neck, and he put EMG sensors, so electromyography sensors, and the strain sensors on his neck. And he and his grad student colleague went to MD Anderson. This was actually just 2 weeks ago, so this is fresh, unpublished data. We had 17 laryngeal cancer patients in the trial. 7 had already developed dysphagia, so difficulty swallowing, and 7 had not. And I won't talk about this in too much detail, but the upshot here is that the difference between the strain, so just the stretching of the skin, and the electrical signals are actually different between opening the mouth and swallowing and talking. So we can actually use what's called a machine learning algorithm on a computer to differentiate not only a swallow from a not swallow, but also swallowing different types of food. So you can detect the difference between swallowing a cracker from swallowing air or yogurt or water. So we're pretty excited about this, and in particular, we're going to compare this to the gold standard treatment, which is going to the hospital to get a video X-ray of some heavy metals going down your esophagus, which isn't very pleasant. So we're hoping to be able to do this now with a home device. Now, our interest in wearable sensors started to develop into an interest in touch and in human-machine interactions. So one of the first ideas that I had was to take a glove that has some strain sensors on it that could be the graphene nanoparticle sensors or some other type of sensors. Maybe we don't need that much sensitivity, and to be able to sign the letters of American Sign Language and translate those signals into letters that would appear on your smartphone. So this is what my student came up with, and I will not be responsible for exactly every piece of the printed circuit boards here, but this is what he came up with. This is a golf glove with some strain sensors on the knuckles, which are the black pieces of conductive polymer, and the electrical circuitry that ends up being able to differentiate the letters. So these are the letters of sign language. Some of the letters can be differentiated only on the basis of bent and unbent knuckles. Some of them, however, like I and J, have a motion and give you the same code whether you have an I or J, except that there's a motion involved. So we need an accelerometer as well. There are other letters too that require pressure sensors to differentiate. So my student did all of that and came up with what we call the Rosetta Stone of the American Sign Language alphabet with this glove. Now all of these red lines here correspond to changes in resistance due to bending and unbending of the knuckles. And if you have a computer program, you can read out the combinations at each point, combine it with whether or not the hand is moving, and you can get the letter. So this is what it looks like, and that's the output to my student's iPhone in the top left corner. And we call this project the language of glove. And this paper was just provisionally accepted 2 days ago by the journal, so we're pretty happy about that. We can also take these data and we can output them to virtual reality. So this is a hand that is constructed of a molecular model kit, as you can sort of tell here, and the data that the real data from my student's hand is being output directly to this virtual hand, and you can wear virtual goggles and you can see this in the virtual environment. Now it's behaving a little squirrely here, and that's how you know they're real data because the student is just learning how to make these signs. Now the problem here, the limitation here, is that this glove in a virtual environment is blind. It's numb. It can't feel anything because it's covered in a glove. So what if you were to put actuators on the inside that could send signals to the skin that the device was actually that the virtual hand was feeling in a virtual environment? So this hand picks up a virtual Coke can. Does it feel stiff and cold, for example? Can you make it feel stiff and cold? So now we had to go sort of in reverse, from the hand producing a signal to something in the environment producing a signal in the hand. And this was actually the output of this is the end result of a senior design project that my student mentored in the electrical engineering department. And this is the real hand on the left and the robot hand on the right. And let's play it again. So the ring finger, and then the ring finger on the robot moves on the middle finger, then the index finger, and then the thumb. Now at the tips of the robot hand, you have these sensors, and there are pressure sensors and temperature sensors on the robot hand. So if the robot hand goes into an environment and grabs an object and feels pressure, something that's solid and cold, then there are actuators on the glove that will give you a tactile feeling, like pressure, and there also is a thermoelectric device which translates an electrical signal into either hot or cold. So your hand literally will will feel the pressure and the temperature based on the environment that the robot hand is in. So this shows sort of what I'm talking about. Although the key thing is that the key limitation of this video is that you can't feel what the student is feeling on the left. So you'll just have to take my word for it. Eventually, what we'll get to is a scenario like the feelies in Aldous Huxley's Brave New World, where you go into the movie theater and you put your hands on the armrest and you can feel what the characters in the movie are feeling. But until we have that kind of technology, you'll just have to take my word for it. So the question is, what if we had spatial control on the hand? Now we just have it at the fingertips because we have these off-the-shelf components, sort of from Radio Shack, but on the internet equivalent of Radio Shack. And but what if we had spatial control over where they were in the hand and also conformability to the skin? So if we add our stretchability and skin-like properties to these materials, can we enhance the level of tactile feedback that we are able to achieve? So this allows us potentially to explore the intersection between the science of soft electronic materials and tactile perception. And that's really been what I've kind of been obsessed with over the last year or so. And I'm motivated partly because touch is a little bit of an unexplored area, not only technologically, but also artistically. The touch triggers our strongest emotions instantly, and the skin is the body's largest organ. The strongest emotions can be either positive or not positive. Moreover, human culture is replete with artifacts that interact with the senses in order to convey information, trigger a thoughtful response, or add beauty to the world. And we have this idea, and this is art and humanities, right? So the sense of vision responds to painting and sculpture and visual arts. The sense of hearing responds to music and poetry. Taste and smell are often linked together because they actually rather are linked together. And we can think of food and beer, wine, cosmetics, and perfume. But what about touch? Well, there isn't really a tactile humanity. There is a tactile version of the humanities. There are textiles, certainly, and textiles are known to trigger emotional responses, but they're not really dynamic in the same way that art and music are. You have tactile artwork in a museum for the visually impaired, for example, but in those cases, object recognition seems to be the primary goal, not necessarily the texture and the emotional response triggered by the object. So I think there's a big area for exploration here, and I think it really does allow us an opportunity to invent not only a new branch of science but also the humanities. So one of the first questions that we tried to answer was, can we distinguish a surface that has been Scotchgard coated from one that has not been Scotchgard coated, not by spraying water on it and seeing if it beads up or spreads, but just by touching the surface? Can we tell an object? Now, Scotchgard coating is like 100 billionths of a meter thick. So in principle, a film that's 100 nanometers changes other aspects about the material, not just its surface properties. It also changes its perceived thermal conductivity and other properties that are hard to separate from just the tactile sense. So what we did is we took two surfaces. They're single crystal silicon wafers, single crystal silicon discs, basically, that are atomically smooth on the surface. And one of them we oxidized, and the other one we coated with a thin layer of a thin monolayer that has properties just like Teflon, but it's only one molecule thick, as opposed to a Teflon nonstick pan that has like 0.5 millimeter of stuff. This is one molecule thick. And it turns out that we are quite good at determining the differences between these surfaces. These experiments were done in collaboration with V.S. Ramachandran in the psychology department, who's known, among other things, for treatment for phantom limb pain among amputees, and also the science behind synesthesia. So people who can feel, when they feel objects, they taste peanut butter or something, or they see a number 7 and they see it always as red, number 6 always as blue, something like that. So we're pretty sure that we did the data work up right. And what's interesting about this is that if you pattern these little patches of single molecule thick layers on a surface and you scan your finger across, you can actually read digital information from these little patches of materials that are only 1 molecule thick. So this is this sort of checkerboard pattern in the bottom center is the word lab, capital L-A-B, written in the ASCII alphabet, which is the computer digital alphabet that uses digital bits to render alphanumeric characters. And human beings, at least the grad students in the lab, and we did get IRB approval to do this, that the students in the lab were able to predict about all of the letters about half the time, and most of the letters all but 1 time. So are we anywhere near as good as a hard drive or a CD-ROM reader? Not even close, but this is almost like the human hard drive. We can actually read these signals that are only 1 molecule thick. So we did an experiment to try to figure out how humans are able to do this. So we took a fake finger, and the fake finger was just a piece of silicone rubber, and we dragged it across the same surfaces with a force sensor, and we measured the differences between dragging it across the Teflon-like surface from the sticky or oxidized surface. And what we ended up getting were these plots in the bottom right. Now, these plots in the bottom right are scanning velocity versus force or mass. Same thing on Earth. And if we take the finger and we allow ourselves free exploration of a surface, we can do it at any speed we want and with any downward pressure we want. So these plots here show us in the green and yellow regions the combinations of speed and downward pressure that are more likely to allow us to differentiate one surface from another. So interestingly, it's not just about this static friction that we learn about in high school physics class. It's much more complicated than that. It really has to do with the frequencies of vibrations that you get as you drag your finger across a surface. I think this is it's a very simple experiment, but there's a lot going on. Of course, we determine the difference between objects based on an image that appears in consciousness. This feels rougher than this one. This feels smoother, but it doesn't translate in a simple way to this mechanical contraption that only has just a force sensor on it. It doesn't have a brain. It can't tell. There's no qualia. There's no sense in what it's like to drag your finger across. It only gives you a number or a range of numbers. So can there ever be a gamut of touch in the same way that there is a gamut of images, so a gamut of color? So this projector can render any color that our eye can see, almost any color, based on a combination of red, green, and blue pixels that are illuminated in different combinations. And they trick the light-sensitive molecules in our cones in our eyes to trigger at different ratios, and then it produces an image in consciousness as being purple or violet. And we call this, say, the RGB of vision. Now, is there an equivalence in tactile technology? Can you come up with some number of tactile stimulators, some kind of tactile actuators that arranged in the right proportions are able to reproduce any tactile sensation that you might have? So say suppose, and why would we want to do this? Robotic surgery is ubiquitous technology now in the developed world. What if the human user had precise tactile feedback that actually felt like the biological milieu inside the patient? What if we were able to console premature infants by touching them in the appropriate place in a premature infant ward, for example, without an actual human being present? What if we could reassure comatose patients who are still sometimes aware of some of their peripheral nervous system? What if we can console them even if nobody is there? What if we had Scripps Institution of Oceanography wants to capture an anemone using a robotic hand, but in order to get a metal robotic hand to capture a soft creature, it might crush it. But what if we had human-enhanced robotics, for example? To do that, you need good, accurate haptic feedback, so feedback that interacts with the sense of touch. So can there be an RGB of touch? And this is very much a proposal at this point. In fact, it's being reviewed by a granting agency right now, but I'm going to put it up here. So this is, imagine that you were to reach into a box in a virtual reality environment, and the box was full of round objects. Say a tennis ball, a golf ball, a warm stone, and a basketball. And they differ not only on the basis of their size, but also their surface texture, their bulk hardness and elasticity, and also their temperature, and not only temperature, but thermal conductivity. So the reason why metal feels cold is because it sucks the heat away from your hand faster than, say, a plastic object. So this is sort of the hypothesis for what could be the red, green, and blue pixels of touch. And what I've drawn here are 3 different types of devices, and we're not going to worry about the details, but I'll just explain it as follows. An electrorheological transistor might be a device where if you apply an electric field, its stiffness changes. So that would give us the feeling of coming into contact with an object that had physical resistance to it. An electrotactile device is a device that, using an alternating current, couples to the mechanoreceptors. Those are the nerve endings in our skin that produce tactile sensations in order to trick them into feeling an object or texture. And then we have a thermoelectric device, which is something that we've already shown that we can use, that either heats up or cools down depending on the application, or depending on the object that either a robot hand or a virtual hand encounters. And because I'm a chemist originally, I had some ideas as to how you might make these stretchable electronic components using materials that have the same basic structure as polyacetylene from the first slide, but have a lot of bells and whistles on them that allow them these various properties. Now, I think this is my last data slide, but the idea is one of the materials that we've been exploring is ionically conductive hydrogels. So picture a contact lens that has movable ions in it that can conduct electricity, but it's really through the movement of the ions, not through the movement of electrons. So it's like you take, I don't know who would ever do this, but if you took a contact lens and you put it in salt water, then it would become an ionic conductor. The ions would go into the structure. So can you therefore build an interface that's based not on electrons but on ions? And why would you want to do that? Well, signals are transduced in the body using ions. So it might make a better interface with human biology if we could make a bioionic interface. And my student was inspired by an image that he saw. One of my colleagues at Seoul National University had the robot hand and the human hand, and then my student said, well, let's put my material in between to show the real interface here. So here's our hydrogel. You just pour it out and cure it in a petri dish. And this is a device that's like a thimble. It's about the size of a finger, and you can wrap it around your finger, and it generates a sensation. And the type of sensation that it feels like is kind of like a mechanical tapping. And as you change the voltage, you feel a stronger or a weaker type of tapping. So the bottom curve on the bottom right is the limit of perception. The top curve is the limit of comfort. If you turn up the juice any more than that, it feels rather annoying. And then the green curve is sort of the sweet spot where we would want to be technologically. So this is a skin conformal device. It's made out of the same materials that you make contact lenses out of, and it can transduce tactile information directly to the skin. Now what is the I'm generally interested in societal benefits of basic research, but there's also, of course, an aspect where you want your stuff to matter, and you want it to matter sooner rather than later. So what's the potential impact? What are the market forecasts for these various industries? Transparent electrodes, like for graphene, for example, supposed to be 5 billion. Medical robots is a fast-growing industry. Wearable electronics, even larger. Virtual reality. Now, this is highly speculative because most people don't actually want to wear those stupid goggles, but for some applications, it might be desirable. Particularly for robotic surgery and training and education as well. So we're interested in those applications. Flexible packaging, like graphene. Flexible packaging is a huge industry, but it's starting from a much greater baseline. So the growth rate here is not as much. Solar photovoltaics expected to reach $1/3 trillion by 2020. And actually growing in installed capacity by 60% per year for about 10 years. Pretty incredible. Still a very small amount of the total, but solar is definitely on the rise. What about societal benefits? Fracture-proof, ultra-thin solar modules could dramatically lower the cost of solar energy for off-grid and developing world applications, where we still burn about 1 terawatt. So a little less than 10% of all of the energy used in the world is based on unsustainable biomass, so burning wood and cow manure and trash. Stretchable, wearable, implantable, biodegradable devices, I think, could revolutionize preventive medicine and postoperative care. And organic haptics, these haptic touch reproducing devices for telesurgery, training, education, and tactile therapeutics, I think, could be potentially a big deal. And because I'm a professor, I have to list all my citations, and there they are. So here's some select credits here for the work that I talked about. My group comprises 7 PhD students, 2 postdoctoral scholars, 1 visiting scientist from industry, and about 15 undergraduate students from all over UCSD, from all different departments. And particularly, I'd like to thank Alex Zaretsky, who did the work with graphene. He's the one who started the company in Scripps Ranch. The language of glove and transmission of touch was done by Tim O'Connor, who is actually on the job market in the solar PV industry. He actually also did the hemispherical solar cell and also the solar sticker project as well. Cody Carpenter and Charles Dong, who's a postdoc, did the detection of surface touch, and the ionotactile work was done by Sam Root. So if you'd like more information about me, I'm quite easy to find on Google. My website is just darrenlipomi.com. My YouTube channel is also called Darren Lipomi, or it's user/DJ Lipomi, but if you just type in my name, you can find me there. So I'm now doing something new. I'm posting all of my course lectures there, but I think more interestingly, perhaps, I'm also posting a professional seminar series that is related to what life is like as a scientific researcher in academia now, and what students and postdocs and young faculty can expect as they try to do their work. My work is funded by a number of organizations. In particular, the work on stretchable organic semiconductors and the basic science is sponsored by the Air Force Office of Scientific Research. We've had several students funded by the National Science Foundation. We have some money from, well, we have a significant amount of money from the National Institutes of Health through the Director's New Innovator Award, which is funding the bio-integrated wearable electronics. I'm an affiliate of the Center for Wearable Sensors, which has given us some seed funding through these companies. The Center for Wearable Sensors is a center on campus that has a yearly symposium, and if you're interested in that, you can send me an email. Because it's open to the community. And I'd like to point out a new part of the scientific funding landscape that I'm a part of, and that's Benefunder. Benefunder is a new financial philanthropic product it's a startup that was founded by actually an internet and wireless entrepreneur in San Diego. And the goal is to give people a better experience when they give philanthropically. So $37 billion is given philanthropically by Americans each year, but the rate at which people feel good about their, feel totally satisfied about their giving is less than ideal. It's not actually very high at all. So what Benefunder hopes to do is to connect givers and researchers to causes that they care about. So in fact, we got a donation not too long ago, actually one of the first donations that Benefunder processed, and we took the donor, who was a couple, to the lab, and they got a tour, and the students got a nice thrill out of interacting with them. So I'm really excited about the future of scientific funding through unconventional sources as well. So with that, I'd like to thank you for your attention, and I'd be happy to take